Okay, maybe we'll get started. So it's a great pleasure to welcome Professor Swapan Chattopadhyay for this special colloquium. Swapan is visiting the IASC, but he is also an adjunct faculty member of TIFR at ICTS, and Swapan and others are also going to be organizing this very interesting meeting next month, which will bring together a lot of people from around the world on some of the new ideas in experimental particle physics and beyond. And today we'll hear about one such aspect in some depth, the atomic interferometer. But first, let me just say, Professor Swapan Chattopadhyay is a very distinguished physicist, and I won't, he asked me not to embarrass him, I think, with excessively, but I just want to say that he was the inaugural director of the Cockcroft Center in the UK, and very distinguished particle physicist at Fermilab, and now he is based in Berkeley, but he will be spending some time in India as well. So, so let me, he has a long list of affiliations with Fermi Labs and LBNL, etc., which I will not go into. Currently, he is in physics chair at the IASC as well. Without any further ado,
thank you, Rajesh. Can you all hear me here? Yeah? Okay. It's a nice, cozy little... So center of gravity is to the left. So I think I will stand on this side so you can see the screen a bit better. And so, you know, because all this activity is happening in Fermilab, by protocol, I have to have this slide. And I guarantee you this is not photoshopped. This is the way it looks, of course. You believe me, right? This is the way Fermilab looks. But actually, this particular activity has many masters. Let's see if I can, this thing work here. So battery, yeah, okay, it's turned on, yeah, okay. Well, many masters actually, as you can see, were funded by DOE, Fermilab, Kavli, Moore Foundation, and of course in the United Kingdom, they have their Science and Technology Facilities Council. But I'm, of course, loyal to them, but today I'm very happy that my visit to Bangalore had been planned for 3 years, you know, since 2019, I think, right? I mean, but then I came here for a week to arrange my visit, both in IISc and here, and then COVID hit, so I just could never. So finally, this fall, I'm spending September till December, combination of IISc and ICTS. I'm very privileged and feel honored to be here. So let me start by thanking Rajesh and the faculty at ICTS to invite me to give this talk, special colloquium. I have to thank my collaborators in the MAGIS collaboration. It's an international collaboration. We have picked a very bright young faculty at Stanford to be the spokesperson. Jason Hogan, great atomic physicist, student of Mark Hogan. Rob Plunkett is the manager, project manager from a DOE National Lab perspective. I am kind of the senior. I started this whole business, so they keep me as the founding principal. There are many, many universities, as you can see, from North America, Oxford, Cambridge, Liverpool. And my student, who graduated, first student in this business from the collaboration, Jeremiah was my student, and he's now joined Cambridge through the Kavli Foundation to work on this project. And so I'll give a brief introduction, then I don't have to preach to the choir about Standard Model and what are the challenges beyond it to you guys. Well, I'll just say a few things. Then I will mention, describe why quantum superposition of atoms may be interesting to study some of the aspects of unknown territory of, beyond Standard Model, like dark energy, dark matter. Maybe there's a gravitational wave background radiation from Big Bang, just like cosmic microwave background radiation and so on. Then I'll give a little tutorial on atom. I know there are a lot of optical interferometers here, radio astronomers and stuff, but I'll give a little bit of tutorial on atom interferometry, and then the experiment, and then how this came about in the US country. It was hard work on my part, these large accelerator labs, to actually, beyond LHC, is going to be 30, 40 years horizon. What do the young people do? So I had to push very hard on the DOE and national labs to have laboratory scale, very smart experiment, taking advantage of quantum mechanics, quantum entanglement, and superposition to still, go forward in particle physics advancement. And these fruits of these experiments would come much earlier than cryptography or quantum computer or whatever. Those will come many, many years from now. But on the way, we'd get low-hanging fruits in physics. So it took some time, but it's actually working now. So that is funding this project. So I'll talk a little bit about how it came about. So there's a website at Fermilab. It's called Atoms in Free Fall. You can look into it. Basically, we are using a large baseline gravitational drop of atoms, 100 meters or so. Basically, 3 areas of research. We cannot address everything, but if there is a component of dark matter, dark sector, that comprises particles or ultralight scalar particles, we can probably sense them by their coupling to the atomic transition levels. We can test quantum mechanics at large macroscopic scales, like superposed and entangled states separated by meter or 10 meters in space. And we can probably begin to see whether we could have a tool to at least sense the tremor in space-time metric left over from the Big Bang, which must have a certain spectrum and some power density. And by looking at its characteristics, we may be able to discriminate between different models of early universe mechanisms. So you can look into that website, it has all the details. Basically, we are using that. We know how to make atom interferometers at a laboratory scale of 10 meters very well. We are now scaling it up to 100 meters. Our eventual goal is to go to 1,000 meter or a kilometer in a mine. But if you jump from 10 to 1,000, people will laugh you out of the room. So you have to at least make an intermediate, demonstrate 10 to 100, which is what we will do at Fermilab, and then eventually go to a deep underground mine, 2,000 kilometers from Fermilab. And if that is successful, then we go to space between satellites. So that's the plan. And we're depending on the advancement of atomic clock technology, strontium. People usually use cesium and rubidium, these types of atoms in sort of precision, parity violation experiments and stuff. But we are going with strontium, which has a rich atomic structure, and the National Institute of Standards and Technology, they have actually made strontium to be a pretty stable atomic clock. So we're going to go with strontium, which is difficult to make a strontium source which is cold, but we are collaborating with experts at Stanford to get strontium cold atom sources to actually do this. So this is the picture. This is the big high-rise you saw on my first slide, Fermilab high-rise. Some of you who have been at Fermilab, you know this iconic building, I'm sure. Deep here, 100-meter shaft exists for a previous neutrino experiment called NuMI shaft. We are going to use this shaft to drop atoms, 2 atomic interferometers in here, 100 meters each. It's actually an element of a national program, DOE High Energy Physics Quantum Information Science QuantISED program. Look into this archive article to look into the proposal. Many, as you see, there are many universities, Stanford, Chicago, Northwestern, Northern Illinois, Fermilab and SLAC, 2 major labs, and in the UK we have Cambridge, Oxford, and Liverpool. So it's a nice collaboration across the Atlantic Ocean. So, and as I said at the beginning, we have many masters. So these are the funding agents for our experiment. So let me take a very quick detour. As I said, I don't know how to preach the particle physics cosmology. I grew up in the mountain regions in Darjeeling, so I'm used to the term mandala, which is a Tibetan Buddhist term. I always call the Standard Model Mandala, where you have the 6 quarks and the 3 leptons. the neutrinos that come with them. We have the 4 gauge bosons, which carry the forces, and then we just discovered the Higgs particle, which probably provides us with a mechanism of generating mass. And that's a pretty good model, except 2 aspects of it are still under study, under Standard Model. Nature of the Higgs, its spectroscopy, its self-coupling, and so on. And this is going to be the goal of the, well, we can learn something from the next 5-10 years from the high luminosity LHC, but beyond that, we need to do much more. So people are proposing megalomaniac proposals of 100 kilometer, 100 TeV, 50 TeV and 50 TeV proton on proton facility. I'm not so sure it will be ever funded or not. On the way to the proton, you'll go to the electron route, to electron-positron collider first, and then you go to protons. So that's one thing. And the second thing is the neutrinos. As you know, the neutrino flavor mixing and the mass structure of the 3 neutrinos is quite unknown. And here, of course, you have long-standing traditional Japanese program, T2K, Y2K. The J-Park has a very hefty, very intense proton beam delivering neutrinos, which goes to the Kamiokande deep underground detector, and they're going to upgrade that facility to go to Y2K. And then in America, we have something called DUNE, which is a collaboration with CERN, European institutes, and America. They are going to attack neutrino in a different way. So that's the DUNE. So I just want to point your attention to a recent article by Adrian Cho. It has a clash of the titans, talking about America and Japan going head to head on this neutrino business. But in my opinion, Japan, they have a much stronger, much more intense proton facility. They have a much bigger detector. And if they just give 100% of their beam neutrino, they just, win the game, hands up. Fermilab has no chance. But they cannot do that because they have to distribute the beam to many other programmatic activities. So their time is limited, which is a boon for Fermilab. Fermilab is a different proposal. It has different advantages, long baseline, 2,000 kilometers. But so I think the first results will probably come from Japan, but then complemented by something that we do in the United States. So now, standard model of particles, now let's go to the very large. They are connected. Nowadays, you cannot distinguish between the very small and the very large. They are connected. So the standard model of cosmology is, of course, this Big Bang cosmology, where you have all this, 13.8 billion years ago, something crazy happened. Probably there is inflation, I don't know. It may be a trend to talk about inflation. Then you have this expanding universe, which is probably accelerating faster than we thought. And I keep telling my particle accelerator people that you cannot beat Mother Nature, who did the highest energy experiment 13.8 billion years ago already. And there are remnants and fossils from that experiment today. We just have to be smart to look for the right signals, to study very weak signals and very feeble processes. So in the process, we of course learned that there is this matter energy budget. Normal matter is a standard model describes, dark matter, which is probably less controversial because of the real thing is that you will see the galactic rotational curves don't quite match with the mass field. So there's probably some truth to this. Dark energy is controversial. Some people say this rapid expansion is artificial of the data, trying to be fit into an artificial isotropic homogeneous Friedman model. Could be. Or they say it may be just a constant of nature, cosmological constant, take it and don't. But the problem there is that, Planck did the same thing with black body radiation. He just used the parameter h to fit the curve. That's why we call it Planck's constant. But it was not just a fitting parameter, because a few years later, photoelectric effect, Einstein said that light must be considered as coming as packets of energy with h nu. And then another 10 years, Bohr said, to understand atomic spectroscopy, you have to assume that the orbits are categorized by quantum jumps of the angular momentum. So h became a fundamental quantity. So far, lambda, there is no other physical phenomena where lambda is manifesting. So it's hard to take lambda as a fundamental constant. Yet, could be, it is, but we have to look for a process where it shows up outside of this observation of galactic expansion. Or it could be a manifestation of modified gravity, we don't know. But I'm going to take it for granted that there's something there, and how can you look for it? So, wearing my experimental hat, I don't know, many of you know, or it may not be known to you, when you put numbers in, you look at if you think the universe is expanding slightly more accelerated than we thought, energy density created as it expands is of the order of 6 times 10 to the minus 10 joules per meter cubed. Now, if you really don't know the nature of that energy or force, but if you presume it's electromagnetic, just to get a ballpark idea, if you have an electric field of 12 volts per meter in space, E square, that is the energy density of dark energy, okay? And if you look at what we have done so far in the lab, Casimir force or cold cathode ionization gauge, these are like 10 to the minus 10 newtons per meter, same unit as energy density. So these are almost, we have done them in the lab. So this kind of energy density is not something that we cannot really sense if we want to. Only problem is that it has to be, if it's a DC offset, it's hard to measure something DC unless there's some fluctuations. We believe nothing is constant in nature. There must be some time varying fields that are actually giving us that. So, we will look for AC effects of fluctuations to actually see. So that whole idea is to find ways of coupling atomic systems, nuclear magnetic moment, QED, to the dark sector or dark energy, and look for some kind of oscillation in time at very, very small levels of fluctuations by these clever, quantum techniques to actually see how it, if there's something there. So,
what is the cold cathode? The last thing you mentioned, what is that?
This is we use it in accelerators quite a bit. It's a cathode which is super cooled by cryogenic means, and then you actually ionize the gas in front of it, and then you measure the pressure that comes out of it. We want to go to how low a pressure you can get in vacuum. So we cannot go below 10 to the minus 9 or minus 10 Torricelli's, but we want to go, can we go to the ultimate limit of vacuum in the pipes of a meter long? So we use cold cathode ionization gauge for that. And we have been able to reach almost this level of pressure. Okay, so, and then let me just talk about atomic interferometry. Why we were talking about atoms, we pick out atoms as one that is a quantum in nature, it has atomic transition levels, and we want to make sure that we take advantage of its coupling to the dark sector and gravitational field to tell us something about that's happening that we are not finding in colliders and stuff like that. And basically here, we are talking about atoms falling under gravity. If the space-time metric has a fluctuation due to gravitational field, then of course the falling gravity phase of the quantum mechanical phase of the atom would change, sensing that fluctuation. And if it's coupled to the dark sector through the QCD or QED, then the atomic levels would fluctuate, the alpha would fluctuate, and so you should be able to see transitions that are not quite what you expect. So interferometry of atoms would have signature of both fluctuation of atomic levels as well as fluctuation of the metric on the gravitational wave. So of course the dark matter is a big area. We have not been able to see some of the massive particles we expected at LHC and stuff, but we are concentrating on very low energy. So half the community, cosmological, astrophysical community, think they are massive objects which are dark, maybe dark galaxies, dark sun, black holes, whatever you have it. But the other half, particle physicists think there is some field particles associated with them, could be hidden sector photons, axions, massive vector bosons, and so on. So, and there again, you can look at the effect on photons, or you can look at the effect on electrons or nucleons through the nuclear magnetic moment, if it's an axion, actually another magnetic coupling. So I will only talk about atoms to be used as a sensitive detector of precise coupling to alpha, because alpha is very important for an atom or for transitions. And just very simplistically, you got to, so if you just say there's a scalar field, density of the dark matter mass, you can take a square root of that, that gives you an amplitude of maybe some kind of a long wavelength field, a wave of some sort, and characterized by a certain particle that carries that wave. And of course, they have some coupling to the QCD sector, QED sector, and so on. And you would see a fluctuation depending on how strong the coupling is and the model, and anywhere between fraction of a hertz to 5 megahertz. People have calculated this, and they also keep on calculating. I give you two most recent references. They are not the best papers, but these have been calculated, and people are expecting they can actually calculate what would be the effect of this coupling on the atomic transitions, and we are going to use that to put limits on the atomic interferometry data. And on the gravitational front, we of course have seen coherent gravitational waves coming from two large black holes colliding. You get a coherent metric fluctuation that we detect on Earth. But we are talking about now fluctuations which are not necessarily coming from coherent collision of objects, but fluctuations from the beginning, where space-time was being created, probably emerging from the Big Bang, and there's fluctuations in metric. And that fluctuation will be, of course, very, very small, expected to be 10 to the minus 23 to 20 minus 25 level of strain, power density of the strain at 1 hertz. So this is going to be a very different object. And the question is, what is the power frequency bandwidth? And interestingly, if you look at the gravitational wave, LIGO is based on mirrors put in Earth, so they have Newtonian coupling to the terrestrial noise, and they cannot absorb all the shock below 10 hertz. So LIGO peters out below 10 hertz, and LISA, the space-based one, is very long wavelengths, 10 to the minus 3 hertz and on. In between, there's a big gap, and this is called the mid-gap, and there may be astrophysical sources of gravitational wave, and many theorists believe that the primordial gravitational wave, like cosmic microwave background radiation, cosmic gravitational background, may fall in this region. So we need to have a tool to actually measure this. And that's the tool that I'm talking about, atomic probe. So let me give you a little tutorial on atomic interferometry. There are some people probably not very familiar with it. It's a bit different from light interferometry. So in LIGO, typically gravitational wave has a tensor wave, quadrupolar. Your mass distribution, there will be a quadruple breathing motion as the wave goes through. And if you put two masses on the two poles of the quadrupolar motion, and then of course the wave goes through, you will see a strain, and that will fluctuate at a certain frequency, and you try to measure this as accurately as you can. So LIGO does it by suspending inertial masses like mirrors. They do laser interferometry to know the distance very precisely, and they have an orthogonal arm, which is the reference that keeps your timing as good as possible. In atomic interferometry, you have freely falling atoms, so there is no inertial terrestrial constraint on it. It's freely falling. But you use a laser flight time between two atomic clouds to know whether the flight time is being changed due to a gravitational wave or not. And you use the actual atom itself, the strontium atom, a fantastic clock, 10 to the minus 18 to 10 to the minus 19, delta omega over omega, as your reference. So that is the difference between that. And so basically, you get light intensity fringes in an optical interferometer. Atomic interferometer, you design your laser beam and make that as an optics for atoms. So you can design pulses of light, pi over 2 pulses that can split a beam like a prism, or you can make a pi pulse that can actually act like a reflector. And so you actually split the beam into two, prepare the atoms into two very close states, superposition of two states, split them by this laser beam, bring them back together by this mirror, and then bring them back, and you can actually see matter wave interference, which is density of atoms at the bottom of the interferometer. That's the atomic fringes. Anything that changes the path like gravitational wave, or anything that changes the frequency of the atom, like the transition, would of course change the phase matching, and you will see it mapped onto the fringe. So we use strontium. It's a very interesting atomic structure. Basically, we use one very ground state and a triplet state here. The frequency is 698 nanometer, 1 millihertz. There are existing lasers in that wavelength, so it helps to have a laser that you can use to. So strontium is good atom, stable, and we can find a laser that can actually excite the atom in the two states close to each other, and then use this atomic interferometry. So that's why we're using strontium. And let me explain a little bit how we use light as optics for atoms. If you take an atom in a ground state, shine light, atom can absorb the photon, so it absorbs the photon, but then it gets a momentum kick. So if you have two atoms in two different states, you can separate them. One stays put, one gets a kick. So that's actually a beam splitter. You can also use a laser to actually, from an excited state, you shine a laser, you get stimulated emission, so it absorbs the energy. It does not absorb the energy, it spits out two photons by stimulated emission, but then it actually absorbs the momentum and comes to a stop. So that's actually a reflector. So you use these techniques, and these two states, of course, oscillate by the atomic frequency called the Rabi oscillations, to actually create this interferometer. Let me show you a little bit more pictorially. So here you got an atom in two states. You superpose the two, say one ground state, one very close state nearby. You split them by this pi over 2 pulse. You reflect them again at a later time by a pi pulse. Then you bring them back together again by a pi over 2 pulse, and this is your interferometer. In reality, and what's happening, you have an atom, internal state at a certain momentum p, you actually shine a light, you create two states, p and p plus a k, by that mechanism of absorption and momentum, and this one gets a little phase due to the different wave function of the atom. Then you actually use a pi pulse. Each one gets the kick. This one gets the kick backwards. It stops. This one goes on, and then you actually use again a pi over 2 pulse, and you actually each one splits into two. You can combine the two, and when you look at the probability, you actually see the state p and state p plus k are separated, and they go as cosine square and sine square, typical interferometry of objects. And actually you can see the two wave functions peaking at two places, and you can spatially separate them by the distance you're falling. People have been able to separate them between 1 to 10 centimeters. Macroscopically, you have the same atom here or there, depending on its momentum state. And 100-meter drop, you can actually separate them macroscopically by meter or 5 meters. You could not tell where the atom is, superposition, and so on. So here is just for those of just for fun, because I like when you teach our students, you drop the atom, you split them by laser, you another pulse, you bring it together, put another pulse to combine them, and you bring it back, and okay, so as I said, the phase of the atom is proportional to kz. K is the momentum. You can move it by shining laser pulse into it. You can change k. And z is the distance it falls proportional to t square under Newtonian gravity. But of course, there's a wave going through it, gravitational wave, t square changes, z changes, so you get a phase imprinted on it. So this is a 10-meter atomic fountain at Stanford that works very well, has done a lot of good work. So you're depending on the success of the 10-meter atomic beam technology to scale it up to 100-meter for our stuff. So I'm just going to show you a picture of that. They have done this separation. You can see the two states. This particular experiment, they did 1.4 centimeter separation, but so it all works, okay? So now that's an atomic interferometer, but we're going to use now two of them in a long baseline to actually do a gradiometer to determine waves going through between this. So you imagine two atomic sources turned on by the same laser beam, so they have a common laser beam. And how does that work? And if you imagine atom in ground state and a very close by excited state, so at a certain time, and you send a laser beam and you prepare them in a mixture of the two states. And then you drop them, okay? And of course, then you actually send the pulse and you see that the phase has evolved because the time it took the atom to fall, just phase. Now, because it's time, if there's a gravitational wave, there's an extra time fluctuation there coming from the fact that the time of fall depends on the wave going through, so the distance is changing, and so delta t would have a stamp of the metric of the space. And because it's multiplied by omega, if omega is fluctuating, it will have the signature of the atomic transitions. So now, of course, you also have the phase of the laser, but because we are doing a difference measurement between two sources, and so that cancels out by common mode rejection. So the laser-induced phase in the atom is common to both sources, so you can eliminate that. And so basically what you have then a phase change that is the intrinsic atomic frequency times 2L over C. Two ways it can vary. Either this can vary delta omega A by coupling to funny matter, dark sector can couple to the atomic transitions, or it can vary through a gravitational wave. And that's the trick. So realizing that, we thought that, okay, we now want to scale up 10 meter to a meter. At Fermilab, we have this big, here's a lab, there's a neutrino, 100 meter here, and then we have a plan to shoot neutrinos all the way to underground cave. It's a 4 kilometer deep shaft. So if we can prove something that's good enough at 100 meter, we can then translate it to 1,000 meter, a kilometer, and then we can probably think about maybe space. So that is what motivated us. We thought about it, that it would be exciting to actually do this 1 kilometer eventually with the 2 interferometers and do a laser beam going back and forth and do a clock gradiometer understanding of what's happening in this kilometer length. Of course, all kinds of systematic errors and stuff comes in. I'll talk about that later. Okay, so we looked at it, and it's such a preposterous proposition. You know, it takes a lot of convincing around to actually get. So neutrino, of course, is a deep underground facility will happen because neutrino, that is the only thing America is doing now in particle physics. So that will happen. So that means if we keep our real estate kilometer long shaft open, that is there for us to explore. Then there's already a 100 kilometer, few kilometer shaft there and a 100 meter shaft on campus. And so we probably can plan something around this infrastructure so that beyond standard collider physics and so on, we can do something at Fermilab that can still serve particle physics and astrophysics and so on. I'll give you some pictures here. You see the shaft, a lot of detail. This is actually the top of the shaft. This is the bottom of the shaft. We actually did a lot of analysis in this, a lot of civil construction, even though it's 100 meter. This is the strontium source. We are collaborating with National Institute of Standards in Gaithersburg, Maryland, and Stanford University to create a very stable strontium atom source. That's the same thing. This is a laser thing that goes with it. More pictures of that. The hardware is coming. This is our visiting Stanford lab to see they're actually calibrating the strontium source for us, and then they'll ship it to Fermilab. So we just say, this is me. This is actually, let me just, went forward, yeah. Right. Just to give you an example, this is a laboratory, not so spectacular atomic source, and you will see that you actually put in cloud, you cool it, it stays in the lab for a few seconds, and then of course it dissipates, and you have to do everything in this time of 5 to 10 seconds. You have to prepare it sufficiently cold so that you can drop 100 meters without diverging too much. Typically, these are like microkelvin and 10 to the 6 atoms. We are talking about picokelvins and 10 to the 8 strontium atoms. You can get cooler atoms, but then the number of atoms will be very few. And dealing with Bose-Einstein condensate is very tough. So you don't want to do that level of cold. So we just need cold enough so when you drop it, it does not diverge too much. And because of the motion of the Earth and the Sun, the Coriolis effect and all of that. So this is actually workable. Typical picture of the atom source. Now, it's easier said than done, of course, because as you can see, the gravity is not the same everywhere. There's a gradient of gravitational acceleration. There's a gravity gradient noise, we call it. There's environmental Newtonian noise, highways and trucks and the planes going by, everything. There is a finite Coriolis, 100-meter drop, you see the rotation of the Earth, and so you have to compensate for it. Intrinsic atomic clock stability is a problem. So we have 10 to the minus 18 today. In a few years' time, we'll go to 10 to the minus 22 with 10 to the 8 free strontium atoms at 50 picokelvin. So that will be a good thing to have. And then the laser itself, there's a wave front of the light, and it's interacting with atoms, and it has, depending on the optics, it always has wavefront distortion at very small wavelengths. And the wavefront is very critical for us because it contains the phase and it imprints the phase on the atom. So you have to control the phase on the laser wavefront. So there are ways to control the laser wavefront, okay? Which is equivalent to seismic noise in LIGO, but for us, it is the vacuum chamber. Remember, it's a 100-meter long vertical vacuum chamber at 10 to the minus 10 torr, 15 sections, dust, atoms, all that, everything that can distort a laser pulse. So we have been doing a lot of systematic measurements for the last 5 years on the top of the shaft and at the bottom of the shaft, and you look at the acceleration on the top graph and the gravity gradient, which is on the bottom graph. You see this huge peak, which is the peak of the entire body of the Earth sloshing back and forth with the mass of the water around the Earth. So that is that peak. And then you see all these little seismic peaks of little earthquakes or things happen, tremors happening. So we are identifying all these, systematizing it, and this is actually the gravity gradient noise, looking at the phase shift in the laser wavefront. So this is all being categorized. We actually also look at how does it go 100 meters, is still subterranean, and kilometer would be quite subterranean. If there's a wave coming in, seismic wave, how does it attenuate from the surface wave to the body wave? We understand the spectrum of that. So a lot of systematics have to be done before so that you know what you're dealing with, average them out, and then you actually measure. We have 4 configurations of the thing. One is the maximum drop. You drop and you drop 100 meters. You can also do a fountain. You go 100 meters and 100 meters, or 200 meters. Or you can do 2 10-meter atomic interferometers with a 100-meter long baseline. Or you can do 3 of these to actually characterize the background noise. Or you can have 2 species of atoms. See, the equivalence principle had been tested classically, of course. Quantum mechanically, there is no reason to believe that it will be substantially different, but for quantum mechanics, 2 species of atoms are looking at space-time differently. They are distorting the local curvature of space-time. So if you drop 2 species of atoms under gravity, nobody has yet, to a certain degree of precision, been able to say whether they will actually obey equivalence principle up to the final limit of 20 decimal points. So we have the opportunity to do this with 2 species of atoms and do some kind of a quantum equivalence principle. Probably in this 100-meter drop, nothing will happen, but 1,000-meter maybe. So more hardware, filtering the noise, lasers. I'm not going to bore you with the circuit. Time is running up here. Let me now say 2 things. So this business of the background energy, vacuum energy, dark matter, gravitational wave, there's no reason to believe they're the same everywhere in space. So two interferometers at two places would measure very different phase measurements, right? And normally, we measure the phase. We don't quite measure the phase fluctuation, but we measure the square of the phase fluctuations. So if you look at it, experiment, sampling the atom, dropping seconds, 5 seconds, 2 seconds. So the rate is 1 hertz, but the Earth is rotating and you are going in the galactic frame. And so the time difference between the two tells us that whatever signal we get is actually going to appear to us as a noise signal, fluctuation signal. So in the short term, you get 0 in the difference between two interferometers. But over long term, if you wait long enough, you'll begin to see correlations showing up in delta phi square. And so that will tell you space-time correlations of the energy of the field of dark energy or dark matter. So with that in mind, so here is just a pictorial that you see no correlations, but if you wait long enough, and given the fact that you are actually sampling the field in the cosmic microwave background frame, you are actually going to sample these correlations, and eventually you'll get a non-zero fluctuation square spectrum. So, okay. So with that in mind, we convinced UK to have a parallel sister facility. This is called AION, Atom Interferometer Observatory and Network. It's going to be somewhere in England. They have a 10-meter plan in Oxford eventually. They also have an old mine called the Bulby mine, not very clean, very dirty. But we are trying to do complementary experiments between these two. One in Chicago area, then this is in England, okay? So we can cross-check and stuff. And eventually, depending on how these two go, then we have actually a proposal to the European Space Agency to do a satellite-based interferometer. So I am not the one who calculates these things, but there are these phenomenologists and particle theorists who are good at calculating limits and putting bounds and stuff. So given the fact that we are coupling to the dark sector through some kind of a coupling of the dark matter to electromagnetic sector and the quark sector, QCD, they can calculate what is the plot of the coupling versus the mass. We're talking about very light, ultralight, 10 to the minus 14, minus 15 electron volt particles. We are just going to, either they are there or they are not there, but that's all we are going to be able to check here. We're not going to be able to say anything about axions here, really, but maybe. And they put this calculation, 100 meter, it already goes below what they know, and with kilometer, it goes significantly below the sensitivity, and space will go probably over here. If you look into there is a theory there could be a fifth type of a force beyond the 4 type of forces, as BL coupling and stuff. Some young people are actually working on it. You can look at that coupling versus mass, and people have done these plots. And we are seeing that with MAGIS, we can actually reach below what is known already. And if you're lucky, maybe we can even see something there. So that's the dark sector. And the gravitational wave, I would say here, if you look at the advanced LIGO, peters out at 10 hertz, as Lisa, and in this band, 1K, 100, 0.1K, 4K meaning 4,000, and then space, you're actually beginning to chip down in this mid-band, but there's nothing there. So I think that is the plan, and I will just stop here because time is running out. Some people who have been actually collaborating heavily. I will stop here, except that I do want to say a few things about how it all came about. About 3-4 slides, if you want me to. Could I do that? Or the quantum system? And then you can take questions. So what happened is in 2016, I was asked to chair for DOE and NSF and NIST with Ronald Walsworth at Harvard and Roger Falcone at Berkeley, a roundtable discussing that colliders are far away, telescopes are expensive. Can you think about some opportunities in quantum fundamental science, quantum information science and computing? Can we think about quantum sensor that will energize the young people coming out of university, have a 40-year, even though there is no collider, they can be engaged and busy with it. So we did it, and we actually came up with a, typically you come up with a 20-page book, nobody reads it, it gets shelved somewhere. But next year we followed that up with meeting with Google, Microsoft, because these guys are interested in quantum computing, atoms, quids, superconducting cavity. So we were convinced them that, if you are going to get a superconducting cavity-based computer or atomic trap-based quantum computer, that's a long way from now, but on the way, we can help you in particle physics and astrophysics because we actually can draw the low-hanging fruit, making these very precise and make quantum sensors work, and then you can make them in bulk and make them good for your thing. So they bought that and they started to actually created something, and we identified 6 areas where quantum sensors based on atomic superposition, quids, quantum superconducting cavity, new types of materials, topological materials where like Dirac materials, where the band gap between valence band and conduction band is almost 0. So even an insulator, the slightest nudge from a funny particle can turn into a conductor and give you a signal. So we want solid state people to work with us. I think Arindam is here listening from IISc. In November, we are having a meeting with CERN to interact with the condensed matter physicists to have new types of topological materials for detectors. And then we can see new particles, probe the early universe, quantum computers, biosignals like magnetoencephalography, very, very small magnetic signals from the brain, strongly correlated materials, solid state physics, detection of very weak environmental signals. Way before a disaster happens, you can actually sense very small signals. So, all these are very important. And with that in mind, they started a national quantum program. And so this experiment is part of that program, and plan was actually different agencies combined together, West Coast, East Coast, Central States, $600 million per year would be the ultimate goal. And in between mesoscale, they're talking about 6 to 12 prime groups around the country, 10 to 25 million per year for 5 years. And so this was a model that they adopted so national labs can find some meaning without large-scale accelerators. And of course, this is, a lot of applications in detectors, particle physics, training the next generation, education and training, and all this all win, win, win. So I think hopefully, if we are focused on the scientific output without being swept up by the hype of quantum, everything quantum, quantum computing, quantum cryptography, all that, those will come in a long time from now. We got the prize this year, the entanglement. Quantum information people got the breakthrough prize, but I bet you 5 years from now, the quantum information people will get the Nobel Prize probably. But without all that hype, but to really focus on what is the capabilities of quantum sensors that actually take advantage of quantum superposition and entanglement at the very bottom layer, not just a photocurrent detector or everything, of course, measures current and voltage. Some of them just photodetectors, but we are talking about detectors that depend on quantum superposition and entanglement at the very bottom. And then actually your resolution goes up by 4 or 6 orders of magnitude. So that's the plan. And okay, so I just stop here for any questions you may have. Thank you for your time. No, not bad.
Okay. Yeah, sure.
Yes.
Maybe you can turn on the mic there. Yeah.
So I wanted to ask, so you said that these atomic interferometers, they can give you a specific frequency band, which is this mid band. Right? So what part of the design of this?
So it's about
Decides that
few millihertz to 10 hertz.
yeah. So what part of the design of the interferometer gives us this particular band? Anything we use?
So it depends on your atomic, so the atoms that you have available, there are not very many, and you have to have lasers that have to match the atom. So typically only cesium, rubidium, ytterbium, strontium, and these are the atoms that people do atomic physics work where lasers are available. And then you know their stability and you know the actual interferometer. You have experience with these interferometers at various places, including Stanford and Europe and stuff like that. And then you look at that what kind of sensitivity you could get from frequency fluctuations or space fluctuations, and you see that their sensitivity is maximum in this frequency range. Very long wavelength, like LISA, it's very difficult for an atomic beam to sense very long waves that does not interact with it. And very short, like LIGO. LIGO is 10 hertz up, okay? And that's also difficult for atomic beams, technically. If you can have a nuclear interferometer, if there was a gamma ray laser that could excite nuclear energy levels somehow, or may come someday, then nuclear interferometers could actually expand the region somewhere. And anything on the other side is difficult because you have to have molecular masers or something. Maybe I have not looked into it, so I don't really know. Something I don't know to answer. Yeah.
I think Arindam Ghosh had a question. Arindam, please go ahead.
Yeah, thanks, Rajesh. Can you hear me, Swapan?
Yeah, hi.
Hi. So, there's a short technical question. I think we should definitely, there is a lot of commonality in the activities, and I think we should definitely see how we can take it forward. But the question that I have for you is, right now, the interferometry that you showed, the noise is short noise limited, right? I mean, it's, you're talking about when particularly the last part where, you want to check the small number of atoms. Will it, is the short noise the limiting factor there?
We are trying to avoid short noise. Short noise will be important if we go to, let's say, if we go to very, very cold atoms, so it becomes much more precise in terms of the matter wave fringe characterization. But when you have 10 to the 4 or 10 to the 3 atoms as opposed to 10 to the 8 or 10 to the 9, the short noise becomes very high. So although we get a very good atomic interferometer, but the background short noise coming from very few atoms dominates. And so this is why we carefully chose 10 to the 8 or 10 to the 7 atoms per cloud, not too cold, cold enough that it does not diverge, but it suppresses the square root of n fluctuational noise significantly.
Right, okay.
Have I answered your question, Arindam?
Yes, yes. We'll have a chat separately when you are in ISC, so it's, yeah.
And anyway, with the first part of your, so we are meeting in middle of November, Arindam, where you have been invited on 18th of November.
Yes.
With our 7 colleagues to discuss how the condensed matter community and particle physics community can work together to develop the new materials as large-scale detectors.
Absolutely, yes.
Okay, so come, yeah.
Yeah.
Right.
Any other questions, remote or otherwise? So if not, let's thank Swapan again.
Thank you, everybody. Thank you. Thank you.